Welcome back to our discussion about the unit circle. And in this video, we're going to talk a little bit about how we can observe behavior and patterns on the unit circle and what does that mean in reference to periodic functions. So we are looking at the idea of something that's periodic. So first, it makes sense to talk about, well, what does it mean for something to be periodic? And we deal with stuff that's periodic all the time. And really what it means to be periodic is if something has a behavior that we can expect generally after the same behavior after a specific amount of time passes. For example, we know the sun will rise approximately the same time every day, right? So the sun rising is something that occurs after a specific period of time, about 24 hours. We know that it's going to snow about the same time every year if you live in an area where it snows. So about every 12 months, we start a season of cold weather where we might get snow. Anything that we can pretty much rely on happens after a specific period of time is called periodic. So what does it mean for a function to be periodic? Well, when a function is periodic, it means it has an output pattern that repeats after a specific interval. So it may take 2 units for that function to repeat or 250 units for the function to repeat, but it's got a repetitive nature to it. So mathematically speaking, if we are talking about functions that repeat, we can say there is some positive number p, which represents the period that it takes for the function to repeat. And I can multiply that value by any integer, and I should get the same output value as if I had the original function value. So for example, if we knew that the period of a function was 2, that means we would see the same behavior after every 2 units. Well, every 2 units means after 2 units, or 2 times 2 is after 4 units, or 2 times 3 is after 6 units. So f of t would be the same as f of t plus 2, or t plus 4, or t plus 6. They would all be exactly the same value because it would just repeat as a cycle. Okay, so we see some patterns like that existing on the unit circle. And we're going to focus our attention on the cosine function for a second. So think about if we were to start at 0 radians. Okay, here's 0 radians. And okay, so we're going to look at all of the x values that go with these angle measures. Okay, so we're going to focus on the coordinate and focus specifically on the x values here. Okay, so we start at 1. We progress to rad 3 over 2, then rad 2 over 2, then 1/2, then 0. Then negative 1/2, then negative rad 2 over 2, then negative rad 3 over 2, and negative 1. And then back to rad 3 over 2. Oh, I see a repetition there. Okay. But then negative rad 2 over 2, negative 1/2, 0. If I look at all of those all the way around. So how far do I have to go until I find the same x value? Well, here's the cool thing. If I start here at 0 radians, I actually have to go all the way around the unit circle to get back to an x value of 1. Okay, so that is true for if I start here, but if I start at rad 3 over 2, I don't have to quite go all the way. I have to go all the way around until I get here. Okay, but does the pattern start repeating there? And the answer to that is no, right? Because the rad 3 over 2 here is followed by rad 2 over 2. And the rad 3 over 2 here is followed by 1. We want to have the same values in the same pattern. So it takes us one full revolution, one full time around the unit circle for that period to emerge. It takes us 2 pi radians for us to get all the way around. And so that means that if I'm interested in the cosine of t, it will be the same as the cosine of t plus 2 pi times n, and 2 pi here being that period. I can multiply that by any integer that I want, and the output values will be the same. All right, so now let's kind of focus our attention on the sine function. And in this case, we are looking at the y values around the unit circle. Okay, so starting here at 0 radians, 0, 1/2, rad 2 over 2, rad 3 over 2, 1, rad 3 over 2, rad 2 over 2, 1/2, and 0. So it takes me pi radians to get back to 0. But what's the next y value? The next y value after 0 is negative 1/2. But if I start at this 0, my next y value is 1/2. So I've got to have the same y value and the same pattern, but that's not going to happen until I go all the way around the unit circle once. So again, when we're looking at the period for sine, even though we hit that same y value halfway around, the pattern doesn't actually start repeating until you go the full way around. So the period for sine is 2 pi. And so that means that the sine of t will be the same as the sine of t plus 2 pi n. Now, tangent is a little bit special, and it always is a little bit special because it kind of combines sine and cosine, right? But let's go ahead and look at the tangent function. If I start at 0 radians and I'm thinking about tangents, oh, it's harder to do when I don't have them labeled, isn't it? But your tangents, let's think about what your tangents are. Tangent here is 0. Tangent here is rad 3 over 3. Here our tangent is 1. Here our tangent is 1. And here our tangent is rad 3. Here it's undefined. Okay, so we're looking for kind of that progression of tangent. And we can tell you right away that that's not going to happen here because all of these tangent values are negative. But if you look at this third quadrant, it ends up that the pattern for tangent has the same values in the same order starting here, right? Because our tangent here is 0. Our tangent here is rad 3 over 3. Tangent here is 1. And our tangent here is rad 3 and then undefined. So it only takes us pi units around the unit circle to find the same value and for that pattern to start repeating. And so this means that the period for tangent is pi. So similarly to sine and cosine, the tangent of t will be the same as the tangent of t plus pi n. So the difference here just being that the period is pi instead of 2 pi. Here I've taken a second and summarize the periodic behaviors of the 3 main trig functions. Your sine function has a period of 2 pi, which is the same as 360 degrees, right? And so we can express that as this relationship, the sine of t is equal to the sine of t plus 2 pi n, or 360 degrees times n, where n is any integer. Now, similarly, that's true with cosine of t. The period is 2 pi, or 360 degrees. And these relationships hold as well. Now, the only one that's a little bit different then is tangent, because tangent has a different period. Period is pi. And that's why we can say the tangent of t is equal to the tangent of t plus pi n. So how do we use those periodic properties? We are going to think of things that have the same cosine by using the periodic properties. The cosine of 405 degrees will be the same as the cosine of 405 minus 360 degrees, because if I put a -1 in here for n, I will be subtracting 360 degrees. So the cosine of 405 degrees is equal to the cosine of 405 degrees minus 360 degrees, which is the same as the cosine of 45 degrees. And we know that from our experience with the unit circle to be rad 2 over 2. So what about the sine of 11 pi over 4? Well, we can think about that with the same periodic mentality, right? We know that the period is 2 pi, so we can say that the sine of 11 pi over 4 is the same as the sine of 11 pi over 4 minus 2 pi, which is the same as the sine of 3 pi over 4. And we know that to be the square root of 2 over 2. Now tangent. All right, so now as we're thinking about the tangent of 450 degrees, remember that's the one that has a different period than sine and cosine. This one has a period of pi or 180 degrees. So if I'm thinking about the tangent of 450 degrees, I want to think of that as 450 degrees minus 180 degrees. But that doesn't get us as far as we'd really like. So we're going to actually subtract 180 degrees twice. So we have the tangent of 450 degrees minus 180 degrees minus 180 degrees, and that's going to give us a tangent of 90 degrees, which we know to be undefined. And then lastly, if I'm thinking about the cosecant of 13 pi over 6, cosecant is the reciprocal of sine, so I'll use the periodic properties there. So the period is 2 pi. And I can say that the cosecant of 13 pi over 6 is the same as the cosecant of 13 pi over 6 minus 2 pi, which is the cosecant of pi over 6. Now, I don't have these memorized, but I do know that the sine of pi over 6 is 1/2. And so the cosecant would have to be its reciprocal, which is 2. All right, that finishes up our discussion on the unit circle, and I'll see you next time.